So students, in this video we will cover the topic dimensions and its applications. So first of all we will study about dimensions. So what are dimensions? Here's a definition. So dimensions of a physical quantity are the powers to which fundamental quantities must be raised to represent that quantity completely. So what does it mean? Here is an explanation. So all derived quantities can be expressed in terms of some combination of 7 fundamental, or you can say basic quantities. So what does it mean? As we all know that there are two kinds of physical quantities, basics and derived, and all the derived physical quantities can be expressed in terms of basics. So to express the derived physical quantities in terms of basics, we have to raise the powers of basic physical quantities, and the powers to which basic physical quantities are raised are called dimensions of that derived physical quantity. So clearly we have to see the dimensions of basic physical quantities first, then we'll go for the derived physical quantity. So here we have dimensions of basic physical quantities: length L, mass M, time T, capital T, current capital A, temperature capital K, luminous intensity CD, amount of substance mole. And one more thing, that dimensions are denoted by a square bracket. So all these alphabets are written into a square bracket, you can see here. So these 7 fundamental dimensions of fundamental quantities are used to develop dimensions of derived physical quantities. For example, if you want to determine the dimension of any derived physical quantity, like we have force, F is equals to ma. So acceleration means rate of change of velocity over time. So in velocity, what does it mean? Velocity means distance over time. So distance over time over time. So finally it becomes mass into distance upon t square. So here you can see that force is being represented in terms of mass, distance, or you can say length and time. So all are basic physical quantities. So if we will write the dimensions of these basic physical quantities, then what should be the dimension of force? Mass is represented by bracket M, distance or length is represented by bracket L, and time has dimension bracket T to the power 2. So if we combine all these, we'll get M L T minus 2. So this is the dimension of force. Okay, so it's an example to develop dimension of any derived physical quantity. So on your screen there are several derived physical quantities with their dimensions. Now, next topic is applications of dimensions. So here you can see 3 types of applications are given: to check the consistency of any physical relation, unit conversion, to derive a relationship between different physical quantity. All these applications are very important. So first we'll talk about the first application, that is to check the consistency of any physical relation. Since we have studied that physical quantities have their dimensions, but there are several physical quantities which are dimensionless, including some constants. So generally constants don't have any dimension, but there are some constants which have dimensions, like G, capital G, gravitational constant, Planck constant, H, 1 upon 4 pi epsilon naught, which is Coulomb constant. These constants have dimensions, but constants like pi, exponential E, and etc., these quantities are dimensionless. So okay, so let's start the first application of the dimension, that is to check the consistency of any physical relation. So How to check that any physical relation is correct or not? So here's a basic rule, that dimension of the left hand side terms must be equals to the dimension of right hand side terms. What does it mean? If we have a relation that A is equals to B plus C, then dimension of A must be equal to dimension of B, and dimension of A must be equals to the dimension of C also, because here we are using two terms. So dimension of A must be equals to the dimension of B, and dimension of A is equals to the dimension of C. Let's consider that we have another relation, A is equals to B into C. So dimension of A must be equals to the combined dimension of B dot C. So this is the basic rule. Let's consider that we have F is equals to MA. This is a physical equation or a relation, you can say. To check the consistency of this equation, we'll write the dimensions of each term involved in it. So what is the dimension of force? ML, it is represented by MLT minus 2. Mass has dimension capital M. Acceleration has dimension MLT minus 2. If you combine these two, then you will get MLT minus 2. So easily you can observe that MLT minus 2 is equals to MLT minus 2. So it is consistent or it is right. Then to check this equation is consistent or not, we will write the dimensions of each term involved in this equation. So energy quantities have dimensions ml square t minus 2. So according to the previous rule, we have seen that each term, that half mb square and mgh, both must have the same dimension. So let's check. It is a constant, arbitrary constant, or arbitrary constants don't have any dimension. So we'll write the dimension of mass, that is m, and v square means lt minus 1 to the power 2, and height means h, means length. So if you generalize these combinations, then you will get m l square t minus 2, and here you will get m l square t minus 2. So, and in the LHS side you can see it is m l square t minus 2. So each term involved in this equation has same dimension. So this is all about the consistency of the dimension exercise. Here are some examples of dimensions, and hope you will solve it. So students, in next video we'll study about some other applications of dimensions. So thank you.